Hello all. Welcome to the lecture series in applied chemistry, polymers. So in the previous series, we discussed introduction to polymers. And now in polymers, we discuss thermal properties of the polymers. So as in the previous session, we discussed thermal properties of polymers. Somewhat it depends upon the structure and its chain and type of the polymerization process in which it underwent. Uh, and there are some peculiar properties which we need to discuss about how the in a lay words we can say plastic or polymer will behave in different thermal conditions. So the polymers have diverse thermal properties that influence their processing, applications, and performance. So there are some thermal properties I can classify like this as number one, the glass transition temperature, and number two, the melting temperature, number three, thermal conductivity, number four, the heat capacity, like that, and thermal expansion coefficient, decomposition temperature, thermal stability, flammability, etc. So we discuss it one by one, in which glass transition temperature. So it is a temperature in which a amorphous polymeric material that transition from its hard state to a glassy state or rubbery state, soft state. Usually the polymers are hard when we handling, but when we heat it, slightly after some time it becomes soft and rubbery. So the temperature at which this amorphous polymeric transition takes place from a hard to a soft state, we call it as TG. There is a temperature, we classify it as a TG temperature, that is glass transition temperature. So below the TG, the polymer is a hard, rigid, and it also sometimes becomes brittle. And when above the TG, the polymer is more flexible, it becomes rubbery, almost in the molten state. So, for example, polystyrene has approximately 100 degrees Celsius as TG, and polyethylene is 125 degrees Celsius as TG. And what is TM as TG? What is TM? TM is a melting temperature in which a crystalline or semi-crystalline polymer that transition from a solid to liquid state. It's nothing but melting. So here it is transition. That is glass transition means the glassy state to rubbery state. The word itself simply it indicates. And melting means it automatically melts and solid will convert into a liquid state. It's very simple. And polypropylene is 170 degree approximately an example, and polyethylene 130 degree Celsius. And polyethylene you see here 125 degrees Celsius as TG, and just a 5 degree difference, 130 it becomes a TM. Then thermal conductivity, how the polymers conduct. Usually our perception is it won't conduct an electricity, sorry, temperature. But polymers do conduct some amount of temperature. They have a low thermal conductivity. Almost we can say it is no when compared to metals and ceramics, but it has some zero point 0.1 to zero point 0.5 watts like that. So, but the conductivity property, thermal conductivity property can be increased with the crystallinity and filler content. If we had more filler content and we made more crystalline, there is a change in thermal conductivity, which means it indicates that is polytetrafluoroethylene has some changes by adding this to 0.25. Okay. Then heat capacity. The heat capacity is with the amount of heat required to rise the temperature of polymer by 1 Kelvin. Suppose the temperature is 25 degrees Celsius. Uh, Now I'm heating it is it's going to become 26 degrees Celsius. That is 1 degree temperature rise. For that, how much amount of heat I have to supply to it is heat capacity. So amorphous polymers, that is powdery state, with amorphous means which don't have any proper structure. So they usually have higher CP, and the crystalline one have very low heat capacity. Then thermal expansion coefficient, CT. Thermal expansion coefficient means it is good for metals, no? When you heat the metal will expand. So most of the materials which will heat, it will expand. What about the polymers? Polymers expand significantly with the temperature because they have very weak intermolecular force. When we heat, it breaks the weak intermolecular force and it tries to break down and move away from one another, and the expansion takes place. For example, the polyethylene has a high thermal coefficient, expansion coefficient, to 110 to 100 to 200, 10 to minus 6 degrees Celsius. Then what about the decomposition temperature? So decomposition temperature means it's completely disintegrate and break into smaller things. So typically, most polymers above 200 degrees Celsius, they will undergo disintegration. But with the help of some structural changes, as we discussed, that linear, cross-linked, like that, and with the addition of some additives, the decomposition temperature may vary. PVC, polyvinyl chloride, which our pipes and all, no, our PVC pipes, we hear that they decompose at 200 degrees Celsius by producing HCl. They withstand up to 200 degrees Celsius. After 200, they undergo a decomposition. While undergoing a decomposition, it is polyvinyl chloride. So, chlorine gas combined with hydrogen and it gives out HCl gases. Then, what about thermal stability? When we talk about thermal stability, influenced by a polymeric structure, as we said, backbonic structure, and a cross-linked three-dimensional structure, and some addition of additives may bring some changes. As I said you in the last session, that the cooking utensils have some black color handles, which is made up of bakelite. Bakelite have three-dimensional covalent bonding structures. So those structures are found to be some heat resistance. The same thing happens here. It's influenced by the polymer backbone structure, and the cross links happens. So it brings sudden change in this. So the aromatic polymers such as polyamides have higher thermal stability when we compare to the aliphatic polymers. So what about flammability? Most polymers are combustible. They can catch fire and something can be made to be flame retardant. For example, polyurethane foams are highly flammable. But polytetrafluoroethylene has flame resistance. So these flame resistance polymers used to make some fire resistant coats, etc. And as a comparison, here the x-axis goes with temperature and y-axis goes with deformation. And there is a two vertical lines, TG and TM, where TG indicates below TG, there is the plastics are in a glassy state, that is in a hardened state. And above TG, it becomes an elastic or a rubbery and loosey state. And after some time, when it reaches TM, that is melting temperature, they will convert into a liquid state. Okay. So these are some thermal properties which is highly useful to understand the properties of the polymers and its applications. So thank you. We in the next session discuss particularly about the TG glass transition, how the glass transition is important and how it is used to understand the applicability of the polymers. Thank you.